Welcome back to Math 1500, Applied Business Mathematics, Connecticut State Community College. In this video, we're going to look at logistic functions and models. A logistic function is a function that isn't used frequently, but when we look at a logistic model, it does track a lot of realities of what we might experience in our business world and in our life and whatnot. But suppose that we were to have a graph. We talk about iPhone sales, and over time the percentage of people who have an iPhone increases. It appears that is increasing exponentially, and it begins to do so. But there reaches a point where as many people as are going to own an iPhone have an iPhone, and the sales start to slow. And actually what happens is that the rate of increase begins to slow. The number of sales might continue to increase, but there is a limit to how high that will go. And what happens in a logistic function is we have not only a horizontal asymptote low, but there's also a horizontal asymptote up higher. In a logistic function, we call that a limiting factor, where this increase is going to be limited and it's going to bump up against the maximum value. Okay, we call that value the limiting value. And the curve actually, notice, looks more like an S than a lot of the functions that we've seen before. Let's look at a model or an example here. A flu epidemic is spreading through the United States population. An estimated 150 million people are susceptible to this particular strain. It's predicted that all of the susceptible people will eventually become infected. Now we know right now, at time t equals 0, that 10,000 people are currently affected. We also know that the number is doubling every 2 weeks. So 2 weeks from now, we anticipate 20,000 people to be infected. Okay, we want to use a logistic function to model the number of people infected. And we're going to use that model then to predict when, to the nearest week, we would expect 1 million people to become infected. Now, if we observe that initially at time t equals 0, 10,000 people are infected, and it's anticipated that 2 weeks later, 2,000, we could use y equals a times b to the x to find the exponential function that we would expect to model this growth. Since the initial y value was 10,000, we know that that's a. So y equals 10,000 times b to the x. Then when x is 2, we expect y to be 20,000. Divide both sides by the 10,000, and b squared equals 2, or b equals the square root of 2. That's what we would expect to happen. We would expect this to increase exponentially, but it actually isn't going to do exactly that. We're told that initially 150 people are infected. I take that back. We're told that initially 10,000 people are infected, and we expect a maximum of 150 people to become infected. Now I put the 10,000 in for P, the 150 million in for N. I know the 150 million people because that's the estimated maximum. That's what N is, that limiting factor. 10,000 is the initial value when T is equal to 0. B to the 0 would be 1. Okay? So when T is 0, B to the 0 would be 1. So I multiply both sides by the 1 plus A. Then I'm going to divide both sides by the 10,000. So 1 plus A should equal 15,000. When I subtract 1 from both sides, A equals 14,999. We can now substitute all of these values in here because we know P of T is N. That limiting factor, that maximum, 1 plus, we just found that A is 14,999, and we found over here to the left that our B is the square root of 2. Okay, so this is the function that I'm going to use to model the increase. The question now is, when to the nearest week would we expect 1 million people to be infected? The question is, when will P of T equal 1 million people? Takes a little while to write all those zeros. Same thing, I'm going to multiply both sides by the 1 plus 14,999 times the square root of 2 to the negative t, but then I'm also going to divide both sides by that 1 million. So 14,999 square root of 2 negative t is going to equal 149. The square root of 2 to the negative t is 149 over 14,999. We could go ahead and do that division, but notice that this is an exponential function where we don't know t. So we can use a log function, log base root 2, because that's the base of the exponent, of the 149 over 14,999. That equals negative t. So back to the calculator, math. I'm going to go down to log base. The base of the logarithm is the square root of 2. And we want to put in here 149 over 14,999. And that equals negative 13.3. So negative t equals negative 13.3, or t equals 13.3 weeks. Okay, so we can use the logistic model to model that data. We would expect after 13.3 weeks, 1 million people are infected. It's going to continue to increase. It'll eventually level off as we approach all 150 million people being affected. Let's look at another function, logistic regression equation, where instead of giving you the regression equation, we actually have the data. The following data shows the percentage of U.S. homes with wired broadband connection as a function of time in years where t equals 0 would be 2000. So t is the number of years after 2000. So 5 right here would be 2005, because that's 5 years after 2000. I can use the calculator to do a logistic regression, just like all of the regressions we've previously done. First, I go to Stat, Edit, I enter the data into the calculator. Now this takes some time, so I've preloaded my data, but you see my X list, 2, 3, 4, 5, and so on, are in L1, and then those Y values, the percentage values, are in L2. And you don't see it, but it does go all the way down to 13 for those. So, to do the regression equation, stat, calc, we're going to go down past all of these other regressions looking for option B, the logistic regression, and we press enter. We're going to store our regression equation in Y1. Calculate that. You'll notice that the calculator gives it back to us a little bit differently. It uses y equals c over 1 plus a times e to the negative bt. E to the b here operates the same as in the function up here, just the b. It doesn't matter for purposes, and here we're going to leave the e in the function, so y is equal to c, 29.2 divided by 1 plus a. I'm going to call a 9.0. 8.997 is 9. 9.0 times e to the negative b. I'm going to fix my fraction bar here. E to the negative 0.49 t. There's my function. What percentage of U.S. homes does this model predict will eventually have broadband wired or wired broadband internet? 29.2 is the maximum estimate. And then finally, in what year would we expect that 29.2 over 1 plus 9 times e to the negative 0.49t, when do we expect that to equal 15? Before I get into that, got my function, my regression equation, I went through, I answered part A, part B. What I didn't do was look at the graph of that. And so you can see, let me first turn off my regression equation and just look at the scatter plot, and you can see from the scatter plot that the data here has an upward curve. It's increasing, it's concave up. But then that rate of increase starts to slow, and even though these data points over here to the right are increasing, the rate at which they're increasing is slowing. Okay, I ran the regression analysis. We turn that back on, and you can see that logistic function does a pretty good job of modeling that data. We could in part C solve for t just like I did above in the previous example, but I want to show you another option with the graphing calculator. Y equals the 29.2 divided by 1 plus 9 e to the negative 0.49t. We also want to know when y equals 15. So I'm going to put 15 in for y2. And we see the graph. And this point right here is where the logistic function will equal 15. Go to second calc, number 5, intersect. The calculator will find that point of intersection. So notice y1 blue, is that blue function your first curve? Yes, press enter. Is the red function y2 equals 15 your second curve? Yes, press enter. And then to make a guess, press enter and notice my intersection. When x is 4.56, when x equals 4.56, p or y will equal 15. Now, x is the number of years after 2000. 4.56 years after 2000 is 2004.56. It's half a year after the end of 2004. That's going to be the year 2005. So I would expect sometime during 2005 that the percentage will reach 15%. Okay, so there's a quick look at logistic functions. I would imagine that most of you watching this video are watching it for purposes of taking my Math 1500 course. When we come to taking a test, pretty much what you're going to be expected to be able to do is like example number 2 here. Okay, so I hope that that's helpful with the logistic. Again, for those of you who are watching for purposes of Math 1500, this video is the end of the first unit, and I hope that you will do well on our upcoming test, and I will look forward to seeing you in future videos when we're on to our next unit. Thank you very much for watching.